Thanks, Duncan. Thanks everybody for organizing this. So I'm just following up on, so Rito gave a talk yesterday about, where he covered kind of the science goals of the BICEP program and where we're going in terms of BICEP Array. So my talk's going to be focused a little bit more on our most recent results that came out back in the fall, which is we call the BK18 results. I'll get into a second about what the details of that are, and what the data processing looks like, and trying to focus on essentially how we combine different data sets in order to produce constraints on R, and try to highlight how our data might be interoperable with other people, right, in the spirit of this meeting. So here's this photograph of BICEP3 down at the South Pole, and actually in the background, in this kind of ground shield that you can see 200 meters away or so, is where, the time of this photo was taken, Keck Array was down there, but that's now the site of BICEP Array. So first off, so I gave a talk at Cosmoglobe last year. At the time, we didn't have the BK18 results out, but there's actually going to be a lot of common things between this talk and the one I gave last year. So apologies for those of you who might find some of this old material, but of course we do have these new results that came out. So when I'm going to use this phrase BK18 a lot, but basically that's just shorthand for all of our data, including and through that 2018 observing season. And so this goes back to 2010 was the first season of BICEP2. So this is 9 years now of integrated data from the South Pole. And of course, over that time, the instruments that we're operating have evolved. So if you look at this most recent results, kind of in terms of how it incremented over the previous results, the last paper would be BK15, so through the 2015 observing season. So we've added 3 years of data, 2016, 2017, 2018. And the highlights, so I'd say the number one highlight is that the BICEP3 is now, so BICEP3 actually first started observing in 2015, but that ended up being kind of an engineering season. It was plagued by some cryogenic issues and problems with some of the optical bandpass filters. But starting in 2016, BICEP3 really hit its stride, and so this new result is the first data release that we have that's included data from BICEP3, which again is a 95 gigahertz telescope, a larger aperture, about twice as big of an aperture as the Keck Array or BICEP2 telescopes, and very, very high throughput, so really high instantaneous sensitivity. So that data is new here. And the other big upgrade is that Keck Array during these years, so Keck Array is a modular array of 5 telescopes. And of those 5 telescopes, 4 of them were observing at high frequency at 220 gigahertz. So if you look back to the BK15 result, there's basically 2 Keck telescopes observing for 1 year at 220 gigahertz. So what we would call like 2 receiver years. Well, here you have 4 telescopes for 3 years. So we've taken that 2 receiver years at 220 gigahertz and added 12 more receiver years. So this is a very large step forward in terms of our 220 gigahertz sensitivity. I put a little asterisk there because the 2 of the telescopes have slightly different pass bands from the other 2. This turned out to be a small enough difference that, after doing some simulations about, what the dust signal would look like at these different pass bands, that we were able to just co-add the data and treat it all as one map with kind of an effective pass band that was kind of in between. There's a small amount of additional 150 gigahertz data that shows up in this result, but it's really just kind of an epsilon change, and essentially there's not much change in our 150 gigahertz maps if you go from the BK15 to the BK18 results. And then the data set that did not make it into this paper, but which we are starting to look at now, is that one of these Keck Array receivers was then upgraded to a 270 gigahertz focal plane. So this was a little bit experimental, trying to operate at much higher frequencies from the pole. and basically, trying to determine whether the dust would get bright fast enough to cancel out the worsening atmosphere. And so there is that data in the can. The 2017 data is probably not really very useful, but the 2018 data we're looking at in more detail now. I mean, we think basically the answer is that yes, this is a useful data set, and it is productive to observe at 270 gigahertz from the pole, at least for this for this low LB mud science. Okay, so I'm going to start by just taking a look at the maps. So these are just figures from from the paper. So these are the BICEP3 maps, and if you look on the left, it's the temperature Q and U maps. So these are very high signal to noise. Active sky area is about 2%. What you see here is the total number of pixels that are hit is quite a bit larger than that. But if you look at the right-hand panel, particularly on the Q and U panels, you'll see that they're deeper in the middle. This view actually doesn't quite do it justice. If you look at like inverse variance, you'll see that even these Q and U noise panels look pretty flat in the middle. But if you look at inverse noise variance, you'd find that there's even it's a deeper region towards the center. This just emerges naturally from the fact that the field of view of this instrument is very large, and so the field of view is actually kind of comparable to the scan throw, and that produces these kind of very naturally, smoothly apodized hit maps. So you end up with an effective f-sky of about 2%, whereas if you just counted pixels here, it's something like 5 or 6% of the sky that we have some hits over. And one thing to note is that this 3 years of observing with BICEP3 and the noise levels that we see here on the right is basically caught up to all of the 150 gigahertz data that we took over many years with BICEP2 and Keck Array. So in this term of like these Keck receiver years, we have something like 18 receiver years at 150 gigahertz. And BICEP3 in 3 years has basically caught up to that map depth at 95 gigahertz. So we're now in a situation where we have very comparable overall sensitivity at 95 and 150. And so these are very deep maps. We'll get to that in a second. So here's the 150 gigahertz maps. As I mentioned before, there's basically no change from BK15 to BK18 here. We added a small amount of additional data, but nothing changes significantly, and that's what we would expect. So flipping back and forth, you can see BICEP3 with a larger field of view covers a significantly larger sky area. And I'll get into the details of that in a second. But you can also see flipping back and forth that we're really measuring the same sky signal in both of these maps at 95 and 150 gigahertz. And so this is measuring CMB temperature Q and CMB temperature and E modes at very high signal noise. And finally, it's 220 gigahertz. So as I mentioned, the 220 gigahertz data took a really big step forward from the kind of limited amount that we had in BK15 up to this now much lower noise maps in BK18. You can see, if you compare the Q and U noise, that of course we are still quite a bit noisier at 220 gigahertz. It's harder to take data at that frequency to the atmosphere. But the other thing to note here, I guess, is that while the signal noise is higher still at 220 gigahertz than we have at 150 or 95, we've now with this data release crossed this threshold where we're getting higher signal to noise in these 220 gigahertz maps on dust than what you would get in the Planck 353 gigahertz Q and U maps. So in terms of our ability to constrain dust in our field, these maps are now are the thing that's driving our result. You can kind of see particularly in this bottom right corner of the U map, you can see that there is kind of visibly some additional dust signal on beyond the CMB E modes, And though I would note that that's, again, because of the apodization of the maps, that's actually in a relatively high noise region of the map that gets pretty downweighted in our analysis. So, most of our sensitivity is really coming in the center of the map. And because of, where we selected our field, that center of the map is has lower dust amplitude than what you see in that bottom right corner. Okay, so this figure I think is a good summary of the sensitivity of those maps. So that the maps themselves are biased. They've been heavily filtered, and so just looking at the say the noise level in those maps is not really telling you what you want to know. But these are band power derived statistics. So they've gone through our kind of pseudo-CL pipeline, been corrected for all the filtering and the effects of the beam and so on. And so this is really a proper look at the sensitivity. And so what's derived here, so that the top panel is just the noise band powers and Sibel, which is equivalent to a map depth. And the bottom panel is the effective F sky as a function of L. So it's basically looking at the number of modes per L bin compared to, as a fraction of the number of modes that you would have if you had a full sky map. And so what you can see, so the first off, I should have labeled this, apologies. Red is 95 gigahertz from BICEP3, green is the 150 gigahertz, and blue is 220 gigahertz. And so what you can see is that the BICEP3 95 gigahertz has very similar noise levels to our 150 gigahertz data. In fact, BICEP3 is a little bit better. The 220 gigahertz data is an order of magnitude more noisy. And you can also see in the lower panel that BICEP3 has somewhat larger sky coverage, right? So the other thing to keep in mind that's been circled here is that, of course, that when we go to very low L, we do have some excess noise at low L, and we also have some loss of modes at those very large scales, which is due to our filtering. So both of those things, are going to have some impact on the sensitivity. But I would note, this is only kicking in this, for the most part, in this very lowest L bin. And so in general, these telescopes are quite good at pushing, their sensitivity down below L of 100 into the region that we really care about for measuring primordial gravitational waves. Okay, so now I'm going to talk briefly about how those maps are made. So this is what some of the raw data looks like. So this is what we would call a scan set. It's about 45 to 50 minutes of data, in which time the telescope is just executing this 60-degree scan in azimuth. And because we're at the South Pole, when we scan in azimuth, that scan is in the direction of right ascension. So the sky doesn't rotate. We're always scanning along the direction of right ascension. The middle panel is showing what you get if you take the detector AB polarized pairs and take their sum to measure temperature. And that shows, atmospheric structure. And you can see this kind of sinusoidal structure because the detectors are scanning back and forth over, lumpy features in the atmosphere. It's highly correlated across detectors, as you can see, though, of course, the signal that's visible here is primarily a very low order signal, and in the filtering that we do in our map making, we're going to remove a third order polynomial for each of these half scans that you see here. That actually wipes a lot of this signal out, but there's still a lot of atmospheric noise in this temperature measurement. But the bottom panel is what you do if you difference the AB polarization, and you can see there's clearly much cleaner. The atmosphere is predominantly unpolarized. We're starting to explore some polarized atmospheric effects that we seem to see in bad weather. But for the most part, this is very clean. And so this pair differencing, the pair sum and differencing, is done with relative calibration that's derived from these elevation nods that we see on the left-hand and right-hand panels. So before and after every scan set, we do a little tip in elevation. That allows us to use the atmospheric signal to do a relative calibration between all our A and B detectors. And that bottom middle panel is kind of the proof of that we've calibrated these detectors off the atmosphere, and therefore when we difference them, the atmospheric signal goes away to a pretty high degree. So just as a note, I mentioned that our maps are heavily filtered. So the maps themselves are, it's very complicated to describe what's the residual signal in the maps themselves. So the filtering that goes on is, as I just mentioned, there's this third order polynomial in azimuth that we fit over each half scan, so about every 30 seconds. And that basically acts as a generic high pass filter. But then over the entire scan set, we fit and subtract any azimuth fixed signal or scan fixed signal. So as we were just hearing in the ACT talk, this could be some ground pickup, but it could also be other sources. So anything that's azimuth fixed, that's not rotating with the sky, we're going to subtract out. We do have, actually for many, many years now, we've been having every two adjacent scan sets are actually scanning over the same fixed azimuth range and at the same elevation. So in theory, we could remove this signal not on a 50-minute time scale, but on something closer to a 2-hour time scale. This would let us push our sensitivity down to lower L a bit, though a lot of work still has to be done to see whether whether that's allowed or whether there'd be like systematic problems that would pop up. So it's been a long-term interesting project that we haven't really had the time to devote much energy to. But then on top of these two filters that I think are things that a lot of CMB experiments have done, we also have a filter that's used to remove some of the instrumental systematics that would otherwise be present in our data. So in particular, if we haven't done quite the right relative calibration of our A and B detectors, then you would not correctly difference away a temperature signal. And so since we calibrate our A and B detectors off the atmosphere, which has a different spectral shape, a different SED than the CMB, there's a potential problem that that calibration could work well for an atmospheric SED, but not correctly difference away the temperature signal from the CMB, which has a 2.73 Kelvin blackbody SED. So we're able to basically, we just use the CMB temperature as a template and filter out from our maps anything that follows that CMB temperature template. We can also construct similar templates of the temperature depolarization leakage that we get if your A and B beams were offset. So there was some differential pointing. And we also work on the differential ellipticity. These are kind of quadrupole terms. For that, we use not a deep projection, but rather we just measure these terms with beam maps and subtract what we believe is the exact temperature depolarization leakage systematic. But all three of these things mean that the maps are quite complex in terms of understanding what signals are present. So you can see this if you look at the maps in Fourier space. So this is the 2D Fourier transform of one of our Q maps. The kind of overall cross shape that we see here is just the E mode signal in Q. But you can see kind of highlighted with this box that there's this kind of trough down the middle, this missing power. And that's because of the fact that our scan is always in the right ascension direction. Therefore, our filtering is highly anisotropic. So we're primarily filtering out modes that have small values of small values of the wave vector in the X direction or the RA direction. However, a really kind of important piece of technology that we have in our pipeline to deal with this is this thing that we refer to as our observation matrix. So because all these filtering operations are linear, you can represent them all in a big matrix. And so this matrix would then transform the true sky to the sky as observed by BICEP. And it involves, it includes the effect of the polynomial filter, the ground subtraction filter, and the temperature depolarization leakage deprojection. And so a nice thing, for people who are maybe interested in using our data and our maps is that this provides a relatively portable description of all the complicated filtering that goes on in the maps. I say relatively portable; it's like a 60 gigabyte matrix or something, but it's it's manageable. And so an example of the use of this is actually I should have probably included like a whole slide about this, but like Ben Thorne and Marius Malaya, some folks at UC Davis, who are part of the SPT collaboration, but are now in a close collaboration with us, have been building like an entirely separate data analysis pipeline, following very different methods, this kind of fully Bayesian approach to the analysis. And they're making heavy use of this matrix so that they can forward model any sort of signals into, and figure out what those signals, how they would show up in the BICEP maps. And so this observation matrix, while it's, it was developed and is heavily used in our kind of standard pipeline, which is operating in a pseudo-CL kind of pipeline, it's a really useful tool that can be employed for very different styles of analysis. And I know like Rayo Cascatalo has been porting this kind of machinery to SO for use with the SO sats, and it's also going to be used, I think, in CMBS4 with the small aperture telescopes there. Quick note about noise, since we heard such a good description about the noise modeling that's being used for ACT. So we're working with we use actually noise pseudo simulation. So because our ScanSat strategy is extremely redundant and repetitive, we can take those scan sets that I showed you and basically combine them all with random plus and minus signs to produce a simulated map where the sky signals have all been canceled out, but the noise is still present. And so this is going to naturally include all the detector correlations and so on. And you can actually show, it turns out mathematically, it's mathematically equivalent to doing basically a cross-spectral analysis, though with a large number of splits enabled by the fact that our scan strategy is so repetitive. Here's a quick just view of what this observation matrix looks like. I'm going to kind of, I think, not dwell on this because I'm probably running late, but it is basically this very sparse matrix that takes this kind of, the x-axis would be some input HealPix map, and then projects that into the BICEP pixelization, and also includes all the filtering and so on. So the fact that these QU bands are quite a bit thicker in terms of they're less sparse in that polarization direction, that's actually a direct consequence of our that temperature to polarization leakage deprojection filter that I was mentioning. So then the kind of last stage of our analysis is a likelihood analysis, how we do our component separations. So we don't actually try to produce a component separated maps of the CMB and dust and synchrotron, for instance, but we simply just work with a full set of auto cross spectra across all our frequency maps and fit that to a parameterized model that contains CMB, but also the foregrounds. And that, of course, the results are going to depend on the accuracy of this model. And so we've explored extensions to the model. So in particular, worrying about things like spatial variation in the spectral index that would lead to decorrelation of the dust signal. And so that's kind of an evolving work in progress. And we assume that as our signal noise gets better and better, we're probably going to be forced to introduce additional complications to the model. So then the last thing I would mention that's an important thing here is studying the systematics. So we do extensive deep beam maps of our data and really worry a lot about some of the optical systematics. So what you're seeing on the left is data beam maps at 95, 150, and 220 gigahertz for Keck Array. And this third row is what you get if you difference the A and the B beams. And you can see this dominant systematic is a dipole effect that we get from a mispointing of the A and the B beams. But as I mentioned before, that's an effect that we can remove through this deep projection filter. And you get down to the bottom row, which is essentially what's the residual that's left over after you've done all this deep projection. And as you can see, there's still stuff here, right? And this has still been measured in the beam maps at high signal to noise. And we can, in fact, simulate what you would get in terms of temperature to polarization leakage. If you take the Planck temperature map, convolve it with these kind of crazy shapes, and you're going to get some leakage of that map into polarization. We can then make simulations of that, as I just said, and take a cross spectrum between those simulations and our real maps, and that gives you actually these blue points with error bars. And you can see that these points are modestly positive, meaning there is some detection of this high order temperature to polarization leakage in our real maps. But once we've measured this, that allows us to figure out what is the systematic effect. What's the bias on R that you might get from this, and so we can have a pretty good quantitative understanding of that systematic. So going forward, it's important with each new receiver that we can characterize the beams at least as well, and have to work out as our sensitivity improves how we can keep pushing this this systematic down. So just jumping ahead, so here's the final likelihood results that we get from BK18. So of course, the kind of key result is in this top left panel, which is the marginalized posterior for R. And so what's in red is the BK15 results, and it's been improved now to the black lines for BK18. So we're now at the point where our sigma R is 0.009, so just under 10 to the minus 2. And we set a 95% upper limit of R less than 0.036. So this is leading constraints in the field right now. Interesting kind of new update in this analysis was that we dropped the Planck prior that we'd been using on the beta dust parameter, so the dust spectral index. And that's what accounts for this fairly significant shift you can see in this beta dust posterior here, is that we're no longer using that prior that was set at something like 1.6. And you can see that, in fact, our data prefers a lower value, something like 1.5. Obviously, there's not a lot of significance for this difference, but it's some hint that in our field, maybe there's a preference for a lower value here. This bottom right panel, we don't really see any evidence of synchrotron at this time. In BK15, there seemed like there was some low significance hint of synchrotron, and that seems like it's gone away with the new data. But of course, this 30-40 gigahertz BICEP array data that's currently being detected, and that'll have very much improved sensitivity to synchrotron. So I think it's very likely that we'll see something once those maps have been fully analyzed. So the last thing I wanted to get to is just the importance of delensing in this analysis. So this BK18 likelihood that I just showed doesn't involve any delensing. We did have a BK paper in collaboration with SBT where we did a delensing demonstration, but there's no delensing in this analysis. So the delensing demonstration was with an earlier data set. But going forward, this is essentially the last BICEP result that won't include delensing. It's really essential for us going forward. So as an example, in this BK18 data set, I just told you that the sigma R was 0.009. We can, if we run simulations where there just aren't any foregrounds, if foregrounds were just not a problem, we didn't have to model them, and we just had the raw sensitivity of our data, that would only improve by a small amount. It would go from 0.009 to 0.007. In contrast, if we turned off CMB lensing, if we were in a universe where the CMB was unlensed and there were no primordial, there was no CMB B modes aside from tensors, our sensitivity to R would drop all the way down to 0.004. So this is a much bigger jump, and the takeaway from this is that in fact our current sensitivity is pretty lensing constrained. So like I said, our future analyses are all going to require delensing. We did do this this kind of proof of concept analysis in the past with SPT, where I think one of the interesting things about that analysis was that actually we produced this lensing template using a phi estimate from the Planck cosmic infrared background measurements. We used estimates of E modes that were kind of combined from BICEP3, from SPT pol, and from Planck, but that this ultimately goes together into a lensing template that we then just include in the stack of maps that go into our likelihood analysis. So we don't try to, just like we don't produce a component separated CMB map, we also didn't try to produce a delensed CMB map. We'd rather use this estimated lensing that goes into that analysis, that goes through this likelihood and ends up in parameter constraints. And this works quite well and kind of just fits in naturally with our approach. So going forward, obviously, we're going to have to keep doing this sort of thing. But with SPT3G on the sky, we're hoping to move forward from no longer doing a phi estimate from the cosmic infrared background, but actually going to a CMB derived estimate of lensing from the SPT3G data. And so that's all in the works. We've really kind of increased our level of collaboration with the SPT folks, where it's now, well, essentially they're now invited to our BICEP analysis telecons. We're essentially getting to a very kind of merged configuration in terms of our collaborations. Okay, that's it. You can again find our data here at this link. In particular, the likelihood module, which is by far the easiest way to combine BICEP3 data with other sets. But hopefully, this was a helpful way to think about other ways that we might be able to use our data together with other experiments.